The modern web browser is designed to handle the friction of authentication on behalf of the user. Once you log into a service, the browser maintains that trust, automatically routing your session data through the pipeline to keep your connection active. Consider a banking application. When you log in, the server issues a session cookie. For the rest of your visit, every request your browser sends to that bank includes that cookie to verify your identity. The vulnerability arises because of how the browser handles multiple domains simultaneously. While your banking session is active in one tab, you might navigate to a second, unrelated domain, like a public forum. If that forum is malicious, a hidden script can trigger a post request, targeting your bank's transfer endpoint, without any visible interaction on your part. Even though the request started on the forum, its destination is the bank. Consequently, the browser follows its standard protocol. It automatically attaches your active banking cookie to the outbound request before it leaves your device. The bank server receives a legitimate-looking request, accompanied by a valid authentication cookie. Because the server cannot natively see that the request originated from a different domain, it processes the unauthorized transfer. This is cross-site request forgery. It is a unique threat because it doesn't rely on a bug in the code. It exploits a core browser feature, the automatic attachment of credentials. Security historically focused on the server's ability to handle data, but as browser mechanics have become more automated, the assumptions we make about the intent behind a request have had to change. The goal of CSRF mitigation is to build a system that identifies and blocks unauthorized state changes, even when the browser is attempting to authenticate them. The traditional approach relies on the application layer. This involves the server generating and verifying unique cryptographic tokens for every form, essentially checking the user's homework for every request. Current strategies supplement this by moving to the protocol layer. By configuring specific HTTP headers, we can instruct the browser to restrict the transmission of credentials based on the context of the request. Creating a resilient application requires a defense-in-depth architecture, a system where the application and the protocol layers work in tandem to verify a user's intent. The first prerequisite for mitigation is method discipline. Any action that changes the state of the database, like a transfer or a password reset, must use post, put, or delete. GET requests must be reserved exclusively for viewing data. Once methods are restricted, we implement the anti-CSRF token. This is an unpredictable, cryptographically strong string that is bound to one specific user session. When the server delivers an HTML form to the user, it embeds this unique token invisibly within the page data. During a legitimate request, the form submits this token back to the server alongside the user's data. When the post request arrives, the server intercepts it and compares the submitted token against the value stored in the active session memory. An attacker on a malicious forum can trigger the request, but they cannot read your bank's HTML to find the correct token. When the request arrives without this unpredictable value, the server drops the connection. Anti-CSRF tokens shift the burden of proof. The server no longer trusts a request just because a cookie is present. It requires a secret that only the legitimate application could have provided. While tokens are effective, they require perfect implementation across every form and create computational overhead on the server. If one form is missed, the protection for that entire domain is compromised. Protocol layer defenses solve this by using the set cookie response header. This is the primary tool used to deliver session rules directly to the browser's credential manager. The same site attribute is the most direct defense at this layer. It allows a developer to define exactly when a cookie is allowed to leave the browser in a cross-site context. Setting same site equals strict provides maximum isolation. The browser never sends cookies on cross-site requests, ensuring forged external requests arrive unauthenticated.
Same-site/lax offers balance, blocking cookies on unsafe methods like post, but permitting them for safe top-level navigations like external links. Because of its security benefits, most modern browsers now default to lax behavior if a developer does not explicitly define a policy. Same-site attributes stop the attack at the source. By preventing the browser from borrowing the user's credentials for external requests, the forgery is neutralized before the packets even reach the network. There is a critical overlap between CSRF and cross-site scripting. If an attacker can use a script to read your session cookie, they can bypass same-site restrictions by manually building a request. To prevent this, we use the HTTP-only attribute. This creates a hard boundary that prevents front-end JavaScript from ever seeing the cookie's value. We also add the secure attribute, which ensures the browser only transmits the cookie over encrypted HTTPS connections, preventing interception on the local network. For high-security environments, we can use cookie prefixes, specifically -host-, to enforce the strictest possible origin boundaries. A browser only accepts a -host- prefixed cookie if it meets rigid criteria. It must be secure, have a path of / and omit the domain. By omitting the domain, the cookie is locked strictly to the host that set it. This prevents malicious subdomains on the same network from overwriting or reading the session token. This combination of attributes binds the session payload to the originating server, ensuring it cannot be read by scripts, intercepted, or manipulated. Modern applications often move beyond standard HTML forms, using AJAX and API endpoints to manage state changes. This enables a final verification layer. Servers can inspect the origin or referrer headers on incoming requests. If the request claims to be an internal transfer, but the origin header points to an external forum, the server can safely reject it. We can also require a custom HTTP header, such as x_requested_with, for all state-changing API requests. This forces the browser to engage its cross-origin resource sharing, or CORS model. Browsers will not allow a cross-origin request to include a custom header without first sending a pre-flight request to ask the server for permission. When the malicious forum attempts the request, it triggers this pre-flight check. The server sees an unauthorized origin attempting a custom header and denies it. The browser never executes the actual post action. By mandating custom headers, developers turn the browser's own security model into a secondary MUT, catching forged requests before they ever reach the application logic. Relying on a single mitigation strategy is risky. True security requires building for the possibility that one layer will fail or be misconfigured. This model illustrates a defense-in-depth stack. For a forged cross-site request to succeed, it must now survive 3 independent security checks. First, it encounters the protocol layer. Based on the same site policy, the browser itself strips the authentication cookie from the outbound request. When the request hits the server, it is blocked again. Because it originated cross-origin, it lacks the custom AJAX header required for state-changing actions. Finally, if those layers fail, the application layer inspects the request body. Finding no valid anti-CSRF token, the server drops the connection and logs the failure. This redundancy ensures system resilience. By creating multiple overlapping points of failure, the compromise of a single layer does not lead to a total breach. These mitigations require constant vigilance. A single misconfiguration, such as an overly permissive CORS policy, can effectively dismantle these defenses and leave the application exposed. The primary recommendation is to move protection as close to the protocol as possible. Every session cookie should be configured with strict attributes to enforce the browser's own security boundaries. Application layer tokens remain necessary to protect sensitive actions and to provide a fallback for legacy browser environments. Engineering a secure web application necessitates a move beyond internal logic. It requires developers to actively dictate browser engagement rules via the HTTP protocol.